beri hamkorliklarida 10 yil bo'ldi.
Let us welcome back to the our afternoon session. The first talk of the afternoon session is the collaborator of Professor Botirov and academician Rodrigo, the Professor Benedict Janel from Weierstrass Institute of Applied Analysis and Stochastics, Germany. The title of the talk is Periodic Behavior in One and Two-Dimensional Interacting Particle Systems.
Thank you very much. Thank you very much for the kind invitation. Thanks for giving me the opportunity to speak to you. I also want to extend my warmest regards to Professor Utkur Rosikov and also Professor Golubyan Botirov, who I had the pleasure already meeting, I don't know, maybe 10 years ago during my PhD in Bochum. So it's been quite a nice collaboration over many years. And I will present something that is not part of that collaboration. It is work with my PhD student, Jonas Köppel in Berlin. And as you said, it's about time periodic behavior in interacting particle systems. So I'm not assuming that you know much about interacting particle systems. So I want to start as simple as possible with the maybe simplest continuous time Markov process. And this is the Poisson flip. So it's the idea is that you have two possible states in this Markov process. The state is 0 or 1. And then if you wish particle, it jumps from 0 to 1. And this should be done in a way that this is a Markov process in continuous time. And there is really only one possibility to make this mathematically precise. And that is to assign independent exponentially distributed random variables along the time axis. So all these blue segments, they are a realization of an independent Poisson clock. And when it rings at a random time, then the particle jumps. And when it rings again, the particle jumps again back and forth and back and forth. So in fact, there is only one parameter here in the game, which is the parameter of the exponential distribution. Let's call it lambda. Yeah? So 1 over lambda is the expected waiting time for one jump to occur. The state space is just 0, 1. So this is the very simple model that I basically have in mind all the time and abstractions of that. So let's make the big jump to the most general picture, if you wish. And that is and that's not the most general, but it's a very general picture. That's a continuous time Markov process now in a compact metric space. And to describe this Markov process, it is very useful to introduce two more objects. So the first object is the so-called semigroup, ST. So in some sense, what you do, and it's very common in probability theory, if you want to observe a stochastic process, you want to do this indirectly by by checking how the process acts on a test function. So this is kind of the weak picture. So you test your process against, at time t, let's say, started in some state eta, against a test function by saying that you check the expectation. And this gives actually rise, because the expectation is linear, to a linear operator indexed by t, and this is called the semi-group. And in order to be able to really describe the process in the full distribution of the process, this test function class has to be sufficiently rich, and it suffices to use the continuous functions. So in fact, this is a good way to describe the distribution of the continuous time Markov process via its semi-group. But on a that mapped to a continuous function.
Sorry, Benedict. Yes.
And so I want to only consider so-called Feller processes where this is continuous. Question? Is there a question?
Sorry, our internet did not good. Please continue. Sorry.
Oh, I'm sorry. Do you want me to repeat?
Yeah, please, a bit.
A bit, okay. So
yeah,
we observe the distribution of our Markov process via test functions. And this test function family should be rich enough. So actually the continuous functions are good. So if you check how the process acts on continuous functions, so you take an expectation of the process at time t against the continuous function, and this is a so-called Feller process, namely that what you see here is still a continuous function with respect to the starting configuration, then you know the whole process. So it's really a one-to-one correspondence between the Markov semi-group and the distribution of the process. So this can be ensured by basically by the Kolmogorov extensional theory. However, this Markov semi-group is still very hard to understand. It's basically not really, you cannot really work with it. So we're looking for an even simpler description of the process. And the simpler description is the so-called generator. And it simply is somehow the infinitesimal change that the semi-group introduces on the set of continuous functions. And this generator is again linear by the linearity of the semi-group. But you have to restrict maybe to a smaller group, a smaller set of functions in the domain. And actually the domain is an integral part of the definition of the generator. So why do you do this? Because the generators are much easier to work with. And in the background, there is a fundamental theorem, the Hilo-Yukida theorem, that guarantees that there's a one-to-one correspondence between the Markov semi-group and its generator. The beauty of the generator can be seen, for instance, if you look for time-stationary distributions. So you have to, of course, specify an initial distribution in order to specify a Markov process, and special ones, fixed points, are time-stationary distributions. And with the help of a generator, it's very easy to time-stationary distribution. It simply has to satisfy this equation for all functions in the domain. So this is one instance why it's so nice to work with the generator. There is a special class of time-stationary distributions, and these are the so-called reversible distributions. They satisfy also a certain self-adjoint property with respect to the generator. And you can easily see that reversible measures are automatically time stationary by just taking, for instance, the functions f to be the one function. So this is really a class of stationary distributions. Not all Markov processes are reversible, but some are, and they're very famous, for instance, in physics models. Okay, so this is the general framework of Markov processes and their generators. In this talk, I want to look at a very special class of Markov processes in continuous time, and they are usually called interacting particle systems. This is a notion termed by Thomas Liggett in '85 in his famous textbook. And the interacting particle systems are a special class of Markov processes in continuous time because they act on configuration spaces. So if you take the lattice, the d-dimensional lattice, and assign to every vertex a color, 1 to q, and you see a configuration. And if you use the product topology, then this automatically is a compact space. And then the interacting particle systems, they share the property that their generator has this specific form. Yeah. The generators have this specific form. And essentially what you see here are the Poisson rates, what was lambda in my initial example. But now this is the rate that tells you how fast you jump from a configuration sigma to a configuration where inside some volume lambda, subset of ZD, sigma is exchanged by another configuration zeta. So basically, you jump from a configuration sigma to a configuration where inside a volume you have a replaced configuration. And this is the jump rate. This is the Poisson clock that randomly rings, and it tells you when to jump to this new configuration. So what is the beauty of this? Under the Hille-Yuchida theorem, the distribution of my Markov process is fully described by the family of transition rates. I will make basically two distinctions here. I want to call a transition rate local if it only depends on a local set. Yeah, so these are local rates.
Later, may I ask one question? This lambda is fixed, no? Lambda is fixed.
This is for one lambda, but the family extends over many lambdas. In the simplest case, the lambda is just 1 point, and that is the update in 1 point. And it can, of course, be every point has an update rate. Yes. On a general level, you might update several states, several vertices at the same time. So it extends over the sum of all lambda.
Yeah, you take sum, yes, sir. Yeah.
Yes. Okay. You can no problem. Please interrupt me at any time. I'm more than happy to fill in the gaps. Okay. So there is a rich family of interacting particle systems that are actually quite famous, for instance, in statistical physics. So maybe the simplest interacting particle system is the independent Poisson flip that I gave you initially. But now I give you the description in terms of a generator. It's simply updating a single site that's indicated by here. So you start from a configuration sigma, and then you flip the rate, which is just independent of the site. It's just lambda. But more famous examples are, for instance, the exclusion process. It is basically a model for the charge transport in a medium. And what the exclusion process is, you just perform independent random walks. Every site that is occupied initially performs a random walk, but there is a constraint. The random walk can only jump to a neighboring site if it's unoccupied. That's why it's called exclusion process. So the random walkers, they walk, but they can only move to a site if they want to, if it's unoccupied. and you can easily see that the total number of particles is then always the same. So that's why it's somehow a system of, let's say, electrons that move through the lattice, but they have some kind of repulsion property. Another famous example is the stochastic Ising model, or the Glauber dynamics for the stochastic Ising model. The Ising model came up a few times earlier, but in previous talks, but on trees, if I recall. Here I'm talking about the Ising model on the lattice, and it's just the Glauber dynamics for the Ising model, meaning the Ising model is kept as a reversible model for this stochastic jump process. You can also see here that interacting particle systems are historically closely related to statistical mechanics models. And this will come up in the second part of the talk. Okay, so I want to consider a certain property of interacting particle systems, and that is called ergodicity, or maybe more precisely, dynamical ergodicity. What does it mean? A system, an interacting particle, and no matter where you start, what is your starting measure, you will always converge weakly towards this fixed point. So that's dynamical ergodicity. I mean, it's a basic theorem in my introduction course to stochastics. Results of Markov chain theory. So you have a unique fixed point, unique invariant measure, and every starting measure converges. So that's the ergodicity. But life becomes complicated in interacting particle systems. It's not so simple anymore because the state space is actually uncountable. So you cannot really use your theory Markov chain initial course, but you have to do more. And actually, it is an open question posed by Thomas Liggett in his famous textbook from '85. If for interacting particle systems, the following is true. If you already know that your particle system has a unique invariant measure, does it necessarily imply that the system is also ergodic? Meaning, is a unique invariant measure enough to ensure that you must converge, not everywhere, you must converge into this unique fixed point? And the literature provides partial answers to this. For instance, in 2011, there was a result that if you abandon a continuous time Markov process, you go to discrete time steps, then you enter the world of probabilistic cellular automata. In discrete times, this is not the case, even in one dimension. They exhibit an example where you have a unique fixed point, a unique stationary measure, but you don't have to converge to it. In the 90s, in two independent papers using also independent techniques, methods, this was shown to be actually true in one-dimensional systems if the rates are local. Yeah. So indeed, in one dimension, and the methods are very one-dimensional. If you have a unique time stationary measure, and the up must converge to this unique fixed point. Yeah, more or less a physics kind of paper in 11 conjectured that this is not true anymore in 3 dimensions. And together with Christoph Kölske in 2014, we could actually prove rigorously that this is not true in 3 dimensions. However, I should say that the rates that we are using in order to provide this counterexample are not quite local. They're very close to being local, but they're not strictly speaking, not local. So it is kind of almost the answer to the question. Okay, but what remained open since then, 10 years, is what about dimension 2? And what about non-local rates? So somehow, is it still true what Mountford, Ramirez, and Varadan say in 1 dimension if you abandon local rates? Yeah. So what is happening here? in 2 dimensions and 1 dimension. And this is exactly where we tried to make progress. And here's our main result. If you are in 1 or 2 dimensions, it is actually possible. So the answer is no. It is actually possible to exhibit a system that has a unique stationary measure, time stationary measure, but it also has non-trivial starting measures that do not converge to this unique translationary measure. More precisely, they perform a rotation. So if you start in one of these starting measures and you use the semi-group, so you somehow evolve it up to time t, and if s is, let's say, 2 pi, you end up with the same measure. So you're basically rotating this family of measures under the evolution. But the rates are not local, and they're unfortunately also not very explicit. So I will go into details in a minute. So this is our preprint from February containing this result. And just to mention this, our system also is somehow irreducible, which makes it more interesting, of course. If you are in a non-irreducible setting, then that's even not possible to have a unique invariant measure. So what do I mean by irreducibility? Basically, if you give me one configuration and you give me another configuration, which is just different in a finite set, then I can go via finitely many steps from one configuration to the other via positive rates. That's kind of the same intuition as in irreducibility for Markov chains, but now for configuration spaces. Okay. So this is our result, somehow filling the gap about ergodicity in interacting particle systems, at least almost filling the gap. Okay, so before I give you some ideas of the proof, let me just mention a few still open problems. So our example is an irreversible system. So the question remains, is it possible to introduce periodic behavior also in a reversible setting? That's an open question. Second question, is it possible, what happens if I go to almost local rates? My intuition would be in 1 or 2 dimensions. My intuition would be you recover ergodicity. Another thing is our rates are not very explicit. So it would be nice to have better examples with more explicit rates. And I know from Jan Swart and other researchers that they're actually looking and working on similar problems, trying to find more explicit examples. Okay. So in the remaining 10 minutes, I want to show you how we construct this example that is not ergodic, but has a unique invariant measure in 1 or 2 dimensions. And this actually brings us to the theory of Gibbs measures, which I think plays a big role in this conference. But now not on a tree, but on the lattice. So it's in some sense also classical theory. So I'm looking at a configuration space, and maybe some of you already know how this works. You start with creating probability measures inside a volume, lambda, with a boundary condition, and it has this famous Boltzmann weight form. So you have these Boltzmann weights. Okay, there's a long story, the entropy minimization, free energy minimization. So these are special measures, a family of measures, and this family is called specification. The energy function H is typically comprised of individual potentials. And if they are summable, then I make sure that this is a well-defined object, these conditional probabilities. So you have a family of conditional probabilities. This construction ensures that they are compatible, meaning that they're somehow a legitimate family of conditional probabilities for an infinite volume measure. And I want to call an infinite volume Gibbs measure precisely a measure for which these prescribed conditional measures are a version of its conditional probabilities. Yeah, so this is the classical idea. You have a compatible family of free energy minimizers on finite volumes, and then the question is existence and uniqueness of infinite volume measures satisfying these famous DLR equations. The most paradigmatic and famous example is, of course, the ferromagnetic Ising model. It lives on -1,1 state space, and it assigns, it favors alignment of spins. So that can be expressed in terms of nearest neighbor potentials, where you just multiply, and you multiply also by the inverse temperature. So this is the most famous example, and there is a phase transition in beta, as many of you probably know. All right, so but I'm not working with the Ising model. I'm working with the so-called XY model, which somehow turned up in the previous talk, but it's now actually it's what is maybe in the classical sense the XY model. The local state space is a sphere, and you have a long-range interaction. So so you have a scalar product and a long-range interaction. So faraway spins, they can interact, but in a weak way. I have to speed up a bit. For the XY model in long range, there's an old result from the 70s that there is also a phase transition of symmetry breaking type. So you have, if your coupling constant is strong enough, you have a continuum of Gibbs infinite volume Gibbs measures. What we now do is we want to discretize this XY model. So what I meant to say is, apart from all the details up here, which I don't expect you to grasp in this short time, what is important is that this generator is designed precisely to perform an infinitesimal of this discretized XY model, long-range XY model. So a big part of the work that we did is to extend the infinitesimal rotation to an actual rotation. So we need to establish the rotation not only infinitesimally, but also for a finite time s. And this can be done. There is a nice trick, a forward-backward idea, which I don't have time to explain really to you. But the message is, indeed, this rotation, it performs a rotation on these extremals of the extremal Gibbs measures of the long-range XY model under discretization. So indeed, I have featured here a rotation dynamics. So the only thing that is missing is it really true that there is a unique invariant measure? So that's the only thing that's missing. The one thing is to realize that this mixture of all these that is also invariant must be this Gibbs measure, this mu star, and we can employ an older result of us. Actually, it's not old; it's from last year, called the dynamical Gibbs variational principle. And the message is really this dynamical Gibbs variational principle tells us that if you give me another stationary measure, time stationary measure, it must necessarily coincide. It must necessarily be a Gibbs measure, and this is the only Gibbs measure that has this fixed point property. And with this, I stop and thank you for your attention.
Thank you very much, Benedict, for our detailed problem. So, okay, any questions, please?
Question?
Please.
Can we repeat your to get your results for models on trees, or because we consider on ZD?
No. I mean, in principle, this technology should also work on other state spaces. For instance, on trees. I guess the phase trees, as we all, as some of us know. So I guess here the symmetry break. I'm not aware. Maybe Utke, you know this. The XY model. It also has a symmetry breaking on trees, I guess, right?
Yes, yes. The previous talk was on trees. Yeah.
Yes. So this part should I don't see a problem why this should not work on trees as well.
Your open questions may be more tolerable on trees. Open
That's right.
questions.
That's right. That's right.
I have one question. What type of difficulty you will have for 3 and more dimensions? Why you consider only 1 and 2 dimensions?
In higher dimensions, there is no difficulty. It's just in higher dimensions, it should be easier to show. It should be easier to be non-ergodic.
Yes.
So in higher dimensions, it's easier to have a unique fixed point and to perform some, let's say, rotations. So the low dimensions are harder.
I see.
And that's why we have to actually go to long range.
Okay. Thank you.
Yeah.
More questions? Okay, if no, let's thank the speaker again.
Thank you very much. Have a great day. Goodbye.
Thank you. Umberto?
Yes, here.
Yes, I'm here. I'm here.
Very good. We can start, I think. So our
Yeah.
next speaker is Professor Umberto Rapero from United Arab Emirates University, UAE. The title of the talk is Sobolev meets Rees. Please.
Just a second. Okay. Can you see my screen?
Yeah, definitely.
Okay. Well, first of all, I would like to thank the organizers to invite me. Well, I'm a little bit far of the topic, but in any case, it's a pleasure, and I hope that maybe next year or soon I will be among you. My talk is Sobolev meets Rees, but why the title? Because we are going to give an alternative characterization of weighted Sobolev spaces via weighted Rees bounded variation spaces. Just a quick outline. We are going to start with some preliminaries. Then we are going to recall some known variational characterizations of Sobolev spaces. And then the last two parts, we are going to introduce the notion of weighted Rees bounded variation. We are going to obtain our result. And in the last part, as an application of weighted Rees bound, and this result, even to the so-called, in the framework of the so-called variable exponent Sobolev spaces and the corresponding variable Rees bounded variation. Okay, now this can be this theorem of Rees, which is quite old. It's from the 1910s, and it can be phrased in modern terminology in the following way: that if we have an absolutely continuous function from an interval into R, it belongs to the Sobolev space W1P, if and only if the supremum of this Rees variation, P Rees variation, is bounded over all partitions. Of course, here is a modern terminology, because in the 1910s there was no Sobolev spaces, but in modern terminology we can describe it in this way. Then this is a quite interesting theorem because it connects this notion of bounded variation with the notion of differentiability of functions even the integrability of the functions in the corresponding LP space. All right, now, since our main goal in this paper is twofold, one is to obtain a similar theorem for weighted solverless spaces in higher dimensions. Okay, I must emphasize this. We now need to introduce some of our notations. Of course, F will stand for a function from some omega subset of Rn into R, and we denote this the weighted solverless space. Of course, as usual, as the set of these functions in the weighted space whose weak derivatives belongs to the same space, to the weighted space, and the norm is given into. It's important always to emphasize, because in general, these norms with weights, they can be introduced either as measures, as in this case, the weight enters in the norm as a measure, or as a multiplier. For our case, we are going to introduce this as stated in 2 as just a weight. Okay, we are going to the so-called A class, when P is between 1 and infinity, it's introduced as we are in the 1970s. Of course, they were introduced by Markenhaupt, and they are quite used in harmonic analysis because they give necessary and sufficient conditions for the boundedness of the maximal operator in the weighted space. We don't need the A1 class here, but it's also possible to define. But the class A infinity is defined as the union of all the classes, because it's known that these classes they enlarge. As bigger the P, the bigger the class, and it contains the previous one, then we can define A infinity in this way. There are other different definitions, but for our purposes, this is enough. Now, some more comments about the weighted solverless spaces. It is known, it's in the literature, that if the weight, if this weight w to the power 1 over 1 minus p is a locally integrable function, then the weighted solverless space is indeed a Banach space. And another important, which once again of the Markenhaupt class, is that if the weight is in this Markenhaupt class, then the weighted solverless space may be defined as the completion of C0. C infinity intersected with the solverless space. And this is a key for our proof, because we are going to use some approximation arguments in our proof. And finally, we want to recall the so-called reverse Felder class. This is the set of all weights which satisfy this condition phi. Okay, we take the supremum over all poles, and this expression should be finite. Now, what is important is that there is a connection between A infinity class and the reverse Felder class. If a weight is in the A infinity class, then there exists some S, which will depend on the AP characteristic of the weight W, such that W is in the reverse Felder class. This is in fact one of the key points of these Markenhaupt classes, because they allow us to reverse the Hölder inequality, and Hölder inequality is one of the workhorses of analysis we always use this. And if you can use it in the in the reverse order, then it's really very it will be a very powerful tool. Now we are just going to touch two known characterizations or variational characterizations of Sobolev space. One of them is of Boyarsky. It is from 2011, and he based himself in this notion of some notion of Sobolev, Bulgarian, Mironescu Sobolev space. But I just want to emphasize or to put this result here to let you know that this is kind of important results that people try to obtain. Then he defines some kind of variation as given in 6, and well, I will just skip all the details, but suffice it to say is that if the function is in some sense has finite variation, then the function will be in some Sobolev space, and also vice versa. Then if the function is in the Sobolev space, then the function belongs to this, belongs to this, it means that it's just finite. Then we have one variational characterization of Sobolev spaces, but this is not the one that we were really interested. What caught our attention was more recent publication of Barza and Lind, and they obtained this result in the spirit of Ries in terms of purely oscillation, the oscillation function. Then if we take any function, then we can define as usual its oscillation on the set A as the supremum. And they obtain some kind of variation defined in the estimates in the equation 7 as the supremum, and now over we have these oscillations over all balls. Well, and the balls they should be inside our omega set, but when I discuss our result, I will give more details. But suffice it to say that this expression 7 and their result states that if W is in the Sobolev space, if and only if our function f can be modified on a set of measures 0 to be continuous, and this variation is finite. And even it's possible to prove that they are equivalent with each other in the sense of the norm of the gradient of f. Well, this is what caught our attention. We tried to generalize this this theorem now into the framework of into the framework of weighted Sobolev spaces. All right, now for this we need to introduce similar bounded variation, but now taking into account that we want some variation with weight. And we notice that if we introduce this variation as in 9, just to do some comparison, here we have p minus r to the k p minus n, and here when the weight is just the identity, then the measure of the ball will be r to the n up to some constant, and then we recover the classical we recover the variation defined above. Now, more information about these balls. Now, the balls, they should belong, they should be contained in omega, right? And the supremum is obtained when we take the collection of all sets of these balls, right? Then we have our omega set. We fix. We have this radius rk. Then we construct all of these balls, and then we take the supremum. Then if if the variation of the function is finite, then we say that f belongs to our BVP, right? This notion of these collections of the balls, they are, let's say, the higher dimensional analog of just a partition. But here we are doing partitions, let's say, through balls. kind of partition. Okay, with this at hand, our theorem reads as follows: that if omega is some open set, as a subset of Rn, and we have that P is bigger than n, this restriction is natural, and the reason is that the proof relies on the Moore inequality, and there the Moore inequality has this restriction. Okay, then this restriction is natural and also appears in the Barzalin result. We cannot improve. And then at least with this scheme of proof, then if the weight belongs to AP such that P is bigger than n times RW, where RW is some infimum is defined above. This is just some technicality due to the proof. Then in this case, F is in the weighted Sobolev space if and only if, once again, we can redefine the function F to be continuous, and F belongs to the space, to the weighted Rees bounded variation space. And furthermore, we have that the bounded variation, the weighted bounded variation, is comparable to the weighted LP norm of the gradient of the function F. Here, all the implicit constants, they depend only on P dimension and the AP characteristic of the weight. Now, I know that maybe the majority are not experts exactly in this topic, and I don't want to go deep because we don't have so much time, but I will just briefly mention what we do. For the sufficiency, as I mentioned, we need to obtain a weighted version of Moore inequality. For those of you who don't already forgot what is Moore inequality, is basically we control the Hilder norm of the function u by the Sobolev norm, which means that we are controlling oscillations in some sense by the Sobolev norm. All right, that's why we need, in some sense, to obtain a weighted version tailored exactly for our purposes, and then we can obtain sufficiency. For the necessity is a little bit more trickier because we need to use some Bezikovich covering theorem, because this is in a sense to try to control the supremum over all the balls. All right, and what we do is we do some approximation of the weighted LP norm of the weak derivatives using sequence of modifiers. Then basically what we do is we are not checking the function f itself. We are going to check the function f convolved with some very good function. We are going to use this to approximate the functions, and then we are going to use the boundedness of the maximal operator, because now we are using a weighted LP space, but because the weight is AP, then the maximal operator is bounded, and this will, in short, it will close the proof. All right. Of course, this is a very, very if you are not expert, I guess it will be a kind of no explanation at all. But this is the main tool. Now, then going back, what we did, we obtained that for weighted spaces, we have the same result of Barza and Lin. All right, then weighted Sobolev spaces, they can be characterized via weighted Rees-bounded P Rees-bounded variation. Now, then, now what we want? Now we want to obtain in another framework, and the framework is variable exponent framework. Now, for this, we need to spend 2 minutes into this notion of variable Lebesgue spaces. Maybe some of you already heard about this. Now, variable Lebesgue spaces, they basically They are generalization of usual LP space where we exchange the power P with some function. But in doing so, we have a problem because we cannot have the norm in the usual way. Then we need to use the so-called Luxemburg norm or Minkowski functional, whatever you want to call it. And we introduce in this way. Then the LP norm, variable LP norm, is given as the infimum over this construction. Okay, this is in fact, this is the Minkowski functional of the unit form. Now, in the same way, we can define the Sobolev space, all right, exactly in the same way. Now, what is important for our purposes, and this theory is already very well known, is that, before we describe a little bit more about Sobolev spaces, we need to introduce some extra conditions. Well, let me just skip. The main idea is the following. In order to have a rich theory, meaning boundedness of some operators, we need to impose some kind of regularity conditions on the exponent P. Now, it was noticed that if we introduce the so-called Lockholder conditions, then we will have a rich theory. In particular, we will have the maximal operator will be bounded. Then we will have the local Lockholder condition, which is stated in 11, and the decay condition or Lockholder function at infinity at 12. All right, these are quite technical, but for the people working in this topic, these are very, very, very standard. For us, what is important is that if an exponent satisfies these conditions, these two conditions, then the space will behave in a nice way. Well, nice, it depends on the context, but let's say this will be the rule of thumb. Now, this class, then there are counterexamples showing that it's not dense. That's why we need to work with this class. And this is just some, well, we don't need this, I guess. Well, this is just the definition of harmonic mean for the function P of x, but we don't need this, I guess. Now, let's then, I need to speed up a little bit. Now we need to introduce that we already know what is variable Sobolev space. It was given in here, the usual. And now we need to introduce the notion of variable bounded variation. Now, we notice that the definition 13 is very appropriate. Okay. Now, what you need to see here is that the powers here are the harmonic mean. Yes. We need the harmonic mean, yes. Then we define in this way. And now we define the variable with bounded variation space, once again, via this Luxemburg norm. All right, the infimum over all lambdas, such that this functional f divided by lambda should be less or equal than 1. All right? Okay, now, but here still defeated step, because D is a fixed, we are taking a fixed set of balls. And now, to get the variable with bounded variation space, now we need to take the supremum over all collections D. Okay, and then we have our with bounded variation space. Okay, now we need to discuss 1 minute about this very, very important tool. This is what is called extrapolation theorem. It goes back to the 1970s, and it's known as Rubio de Francia extrapolation from a Spanish mathematician. It has several formulations, but the one that we need is here. Now, let's just skip all the details here because we don't have so much time. But what is the bottom line? The bottom line here is the following. If we have two pairs of functions, f of g, which means they belong, we say that they belong to a family f. And if we have that expression 15 is valid for every weight w tilde in some set, but here is important, it should be valid for every weight w tilde in this class. Then we can extrapolate that now we have the same relation for the function f and g, but now in terms of their variable norm. Here, of course, we can have f as some operator like tg, and then on the other side we have g. Then this is the way to many people can extrapolate results from weighted classical spaces into into variable exponent spaces. All right, now we are really out of time, but what we obtain. Notice before we do that, we start with weighted spaces in expression 15, but when we extrapolate, we will lose the weight, because the fact that we are running over all weights, it will be the key element which allows us to go into variable exponent. The price to pay is that we will lose the weight, right? No problem in this case. Then we are going to obtain that if f belongs to the weighted Sobolev space, then f belongs to the if f belongs to the variable exponent Sobolev space, then it belongs to the variable exponent Riesz-bounded variation space, and we can control the norm of f, the RBVP norm, with the norm of the gradient of f. All right. Now, once again, the proof runs in a very 1 minute, 2 minutes, and it's over. It runs that we define some averaging operator, and we are going to show that this operator it works for the main theorem for weights, and then we will try to extrapolate. Of course, there are many intermediate steps. We need to prove first that the couple satisfies the conditions just when f is in the dense set. Then we go do approximation, and so on and so forth. And last, we just use limited range extrapolation. And the other one is if f is a continuous function after some redefined it in a set of measures 0, and if it's in this in the Riesz-bounded variation, then also it's in the Sobolev space, and we can control the gradient of f norm, variable norm, by the corresponding norm on the RBVP dot norm, and that's it. Now this part is a little bit more trickier. Okay, I will just skip because I know that we are out of time. But it's of a similar nature. We need to do some kind of embedding tricks first, but once again we are going to use this limited range extrapolation. And the two references given are the ones of Boyarsky and Barzanlin. And if you are interested, this paper was published quite recently in Studia Mathematica. It appears this maybe 1 month ago in Studia Mathematica. Well, thank you, and I'm open to any questions. Thank you very much.
Thank you very much, Umberto. Any questions, please?
Sorry?
Questions from online participants?
Yes?
Okay, in your theorem, you had like P over RW greater than N, yes, in the condition.
Okay, I will share again. Just a second, because yes. You mean the variable or
whatever? In the first one, it was P greater than N. the weighted
Yes.
one, P or RW is greater than N, yes. So without that
Yes.
condition, do you have, I mean, you can have a counterexample, yes, without that condition.
You mean the P?
Yes, yes, yes. P over RW
You mean P?
is greater than N. Not this theorem before the second theorem.
The previous one. You mean the previous one, right?
This
Yeah.
weighted.
Just a second. Yes, the weighted. Yeah, here the idea is the following. Let me explain in brief. You mean this condition here? This condition, it appears why? Yes, the condition appears because at some step, when we are proving Mori inequality, we need to use Hilbert's inequality. And we need to have some space to be able to choose the exponent in an appropriate way. If we don't have this condition, then we cannot apply Hilbert's inequality.
Oh, in that case, if you don't have this condition, do you have like a counterexample to this inequality or what?
Well, I think this should be well known because, as I mentioned to you, this is because of Mori inequality.
Okay. Thank you.
Yes. You're welcome.
Okay. Any other questions, please? If no, let's thank to the speaker again. Thank you.
Thank you very much. Bye-bye.
Our next speaker is Professor Andrei Krennikov from Linnaeus University, Sweden. The title of the talk is Generation of Generic Codes with Two-adic Codon Algebra and Adaptive Dynamics.
First of all, of course, I would like to thank the organizers for this excellent event. And the talk would be about p-adics, non-Archimedean models in genetics and in biology. But they started from p-adic mathematical physics, so the works of Vladimirov and Volovich from Steklov Mathematical Institute in Moscow. And what is the most interesting is that the first conference on p-adic mathematical physics was in Uzbekistan. It was 1988, I think, maybe 1989. It was organized in some nice place, maybe 3 hours by bus from Tashkent. It was organized by Vasily Sergeyevich Vladimirov and his friends from Tashkent. And it was a great conference, and where were established foundations for p-adic mathematical physics. And of course, I remember also great hospitality of organizers. So it's nice to speak again about, at this moment, not already physics, but genetics. But as I told, the origin of this model is in p-adic mathematical physics. So first about genetics code. So people here, maybe majority are just pure mathematicians, and not everybody knows about that in every body, in any cell, we have continuously millions of times our genome used genetic code. And genetic code is still mystery. Mystery is its combinatorial structure. So, and we can try to explain first of all ways the problem. So what is genetic code? Inside our genome is a very long text, which is words are composed of 4 letters, and these letters are for 4 different molecules, which are called nucleotides. It's not important, the chemical structure. What is interesting is that information is not only in one letter, in one nucleotides, but in codons. Codon is a block of 3 letters. So our genome speaks with cell by using words of the length 3. First of all, of course, mystery is why 3, but there are many theories. Nobody knows what is the origin of genetic code. Either this is physical, chemical, or maybe pure just informational, mathematical, combinatorical reasons for this. So genome speak with cell by using codons, 3 letters blocks, and there each codon can encode a block of our protein. So the idea is to produce different proteins, and proteins are composed of 20 amino acids. So amino acids, these are different chemical molecules, the blocks of our proteins. There is also one stop codon in genome. So when there is a reading of the text, each text about protein can have many codons, thousands or millions. And when it's a reading of this text, there should be start and stop. So that cells should understand that there is stop and there is new word for new protein. Okay, so 21 amino acids and 64 codons. So, and now there is distribution of these codons with amino acids. And this is more, the structure of this distribution is mystery. Why it is, I shall show how it looks. And why it is in this way, nobody knows. Even some biologists, in particular one, I think he was from Moscow, Kunin, he even had many publications that it was just random. The genetic code was created in this way and then distributed without any reason. So there is no reason. Other people try to find some reason behind very special distribution of 64 codons to 21 basic blocks for proteins. The picture is the following. So it's not, the table is longer, but my slide was too short. But we can already see the main problem or the main feature of genetic code. For example, this amino acid, it is coded by 2 codons. So the same amino acid, but 2 codons. This is also by 2 codons. But when we go here, this amino acid is coded by 4 codons. So this is 4 or 2. Why it is so, nobody knows. No, there are many theories, hundreds, thousands of papers, but biologists, physicists, chemists, mathematicians, they struggle with each other and everybody suggests his own model. So, for example, there is a lot of models where people try to explain this distribution of codons to amino acids by chemical or physical structure of these molecules. Not everybody accepts them. Not everybody accepts them because they are counter arguments. Others try to even use pure information. That this is what they consider, and this is more or less my approach, that we consider genome and all genetic process as information processes. So chemistry, physics is just hardware, but there is software, and this software has its own mathematical structure, and this mathematical structure is not reduced to physics or chemistry. Some people even think that it is a kind of genetic code, a kind of cryptogram, and here one should use cryptography. So in particular, there was some talks of Luigi Accardi and his permanent collaborator. Unfortunately, I forgot his name. He's also from Rome. They made that some applications of cryptography to the mystery of genetic code. So the basic point for us, where we start, is that there is a possibility to make binary coding of nucleotides. So by coding all these basic letters in our genome by vectors of zeros and ones. So it is not our invention. It was used by biologists. They call this gray coding. And we use this code in the series of works, of my works, Sergei Kozyrev from Steklov Mathematical Institute, and Ekaterina Yurova Exelson, who was my PhD and then 2 times postdoc student. So our idea is that we can treat these vectors, binary vectors of zeros, ones, as two-adic numbers, and then we can use methods of p-adic analysis. P-adic analysis is analysis on trees. As we have analysis on real line, it is more complex analysis on trees. And the Branko Dragovic from Belgrade and Natasha Music, they used more complex p-adic coding for p equal 5. So, as I told, our work was generated by p-adic mathematical physics, and here is names of Vladimirov and Valovich, and also famous mathematical physicists from United States. David also contributed a lot to this topic, and then I started to use p-adics for cognitive modeling because the main idea is trivial. Our brain has networks, and these networks have typically hierarchic tree-like structure. So we can encode processing information in the brain also by p-adic numbers. Yes, so there are reviews on p-adic mathematical physics, and we go through them. Now, another part of our model, p-adic numbers are used for encoding. But then what is the main model, how genetic code is created, is theory of dynamical systems. We consider discrete dynamical systems just iterations of functions. So p-adic dynamical systems, they have many roots. Some roots are from number theory, from mathematical physics. I use them in cognition. Vladimir Anashin used them for cryptography. And recently, I use them for genetic code and biology. And what is interesting, for many years, I had a project with Mexico, with petroleum industry. And here the idea is also very simple. The distribution of capillaries in the ground is also has tree-like structure. And this tree-like, where is tree-like structure, p-adic numbers are welcome. And we also published a series of works on, and they even people from Mexico City, they had grants with petroleum corporations, and they even use them to find better description of reservoirs. Yeah. So now we go to the main slide, of this talk, and this is what I call a tractor model for genetic codes. Here is S because there is no unique genetic code. More or less it is unique. Deviations are very small. So this is another mystery. Why we all, starting with simplest creatures on the earth to us human beings, have the same genetic code with some small deviations. But nevertheless, there are deviations. And these deviations are interesting to understand, for example, who was the first, by using genetic code, we can see the history of its creation, Yeah, so in our model, each amino acid is encoded by a tractor of p-adic dynamical system, given by iterations of function from this is a ring of p-adic numbers, periodic integers, I will explain on the next slide. And this kind of dynamical optimization, so this function make optimization, but field of p-adic numbers, and this in particular ZP is not ordered. There is no order structure. So here we cannot use usual optimization when something goes to maximum or to minimum. So this is optimization, but this is optimization in the sense of stabilization of iterations. So and this are a list of where it was my first idea about a tractor model. There is a big paper in Charles Saliton and Fractals about this model. And Ekaterina, she made a very big step in concrete calculations. So behind this talk is very technical papers. For example, this paper of Ekaterina to find this function. So now the main problem is to find function. Yeah, non-dynamical models works of Branko Dragovic and his colleague Dragovic Anya, and our model with Sergei Kozyrev. So now we're going to the first step. So the binary vector representation of codons. For example, this is used in the gray code coding by many biologists. So first we start with nucleotides. So each nucleotide is represented by vector of length 2. Length 2 is important here. It's more or less our paper also with Sergei Kozarev. Important is dyadic plane, not just dyadic line. So these are all nucleotides are represented by all possible vectors. Then codon is the vector of the length 6. So these are in fact numbers. Then we can encode each binary vector by natural number. For example, if you have such codon, which is represented by this binary vector, this is just this natural number. And now we go to periodics, because of course, in principle, it was even when Igor Volovich started periodic mathematical physics, this was long discussions we had in Steklov Mathematical Institute, that maybe physical numbers are just rational numbers. We can never find, for example, square root of 2 in nature. So all our measurements has finite precision. So we have only natural rational numbers. But why we need, for example, real numbers? Because we need analysis, we need complete metric space. In the same way, we can work on natural numbers, for example, but there is no analysis. So we should embed natural numbers somewhere. One possibility is to real numbers, but another possibility is into periodic numbers. Who are periodic numbers? We fix a prime number, and we can introduce a kind of absolute value or periodic norm, which is defined in this way. If we take natural number, we find the largest order of division of this number by this prime number pi, and send this pi in the degree minus this maximum order of division. Minus, we need to get a kind of triangle inequality. Then for rational numbers, we use this formula, and we get something which is very similar to real absolute value, but with this strong triangle inequality. And this is the basics of all periodic analysis. In some way, when you are experienced, the periodic analysis is easier than real analysis, because this inequality is stronger. You can do more. So we can introduce metric. Then we complete rational numbers with respect to this metric, and we get it would be the field. What is interesting, all operations from rational numbers can be by continuity extended to completion, and these are periodic numbers. So we can introduce the balls. And what is the most interesting, the ball of unit radius is a ring. So this is called the ring of periodic integers, and this ring contains natural numbers, and it's contain our binary vectors for codons. So each codon can be identified with natural number and hence with the element of ZP. Of course, it is important to tell that any element of any periodic integer can be represented in this form of this series. And what is interesting, this series converge. So there's P, K, P in the degree 100 and so on, it's converged. So it gives us periodic numbers. So codons are very special blocks which have only finite number non-zero vectors in ZP. ZP we need to use analysis. Now dynamical systems. So discrete dynamical systems, system is iterations. And we are interested in the limit of these iterations. Then typically it is good to have a measure, and ZP is compact additive group. There is Haar measure, normalized, and we can consider dynamical systems. So this is configuration space, measure, and iteration function. Then we can define attractor. So it's a Borel set or measurable set such that it is invariant. They exist the basin of attractor, some large Borel or measurable set such that iterations that shrinks to this A. And A is the set which is minimal with respect to inclusion. So this is the notion of D13, why we don't go further? Yeah. Oh, okay, great. As usual in the theory of iterations, the exceptional rule is from school, no, from course of functional analysis by Lipschitz functions. So here we also have Lipschitz functions with respect to periodic norm. These functions play the crucial role in the theory of periodic dynamical systems. Especially great contribution was of Vladimir Anashin. Great contribution was of Vladimir Anashin. Now go to genetic codes. So codes are generated through the following process. Each genetic code is created through iterations of corresponding dynamical system. Each its attractor corresponds to the set of codons. It's a kind of cycle which encode of amino acid. As was told, the main problem that we should determine function f only by knowing its attractors. Of course, this is inverse problem and solution is not unique. So we consider just two standard codes. So this is our code in nuclear of our cell, and mitochondrial code. It is code of mitochondria. And we denote the corresponding functions which generate these codes by these symbols. And we have only these restrictions. For example, this is for nuclear code. We have that this, for example, this amino acid is encoded if we go to number, natural number representation or two-adic representation by these numbers. And here they cyclically go one to another. It should be, we want to construct dynamical systems with this set of attractors, and that these numbers inside the cycle will go in this order. There are some reasons for this. And this is mitochondrial code, another set of attractors, and we also want to construct the function. So they are not determined uniquely, and we found such functions by using one minimization condition. So we want to make Lipschitz constant minimal and make representation compact analytic. So of course we can have more terms, but we want to have it as shortest as possible. So, and there are such conditions. So the Lipschitz, the minimal Lipschitz functions which can be approached in this degree, it's the lengths. What is interesting, this was in some way explained to me by Vladimir Anashin, that the functions which we construct are automata functions. So also these are special asynchronous automata. Nevertheless, this dynamics, our model of generation of genetic code is causal, and functions are differentiable, and derivatives are entirely zero. This is the tricky point of periodic analysis, that there exists huge number of functions which are not constant, which has zero derivative. And here I present you the concrete form. It was more or less PhD thesis of Ekaterina Yurova-Axelson. Behind these functions, it's a lot of mathematics. So this is function which generate standard genetic code, and this is linear path. This is linear path. From our idea, it is the oldest, and these are higher order perturbations. This is a function for mitochondrial code, and this is, for example, this example. So how work this function is translate this codon into the same codon. It is we are not in the same, but in the codon in the same cycle. Codon in the same cycle. How we obtain these functions? It's totally beyond this talk because it's very hard technical. We should find functions which has by using 64 points, and they attract cyclic attractor structure. We use very powerful machinery, but very technically complicated of theory of periodic dynamical systems. This is van der Put series. I cannot go even in details. So these functions were constructed due to, and this splitting due to this van der Put series. So these are linear paths, but we still cannot assign real biological meanings to these perturbations. From a mathematical point, it's clear that these are smaller perturbations from two-adic viewpoint, but maybe there's some biology behind, for example, organization or divisions of genetic codes to new genetic codes. What we also found, and this I think can be interesting for biology, For two functions, which I denote defined on this set, and this is the set of codons, we can find how much they distinguish it, so the measure of the closeness. And what we can find? We can find that both these functions, which are linear parts of our coding functions, they're equal to such very simple function, model 2 in the degree. So these are good approximations for both functions. So this simple function is good approximation for both our function. So we have such speculations that maybe there was some common ancestor function, which was very simple, So 32 is just because of this codon structure. Then attractors structure became more and more complicated. And we got perturbation terms. And what is interesting is that mitochondrial code is closer to this function than the standard code. So we can speculate, of course, this is purely mathematical speculation, that we can just guess that mitochondrial genetic code was formed earlier than the standard nuclear genetic code. So mitochondria live somewhere, then appeared our cells, and they kidnapped mitochondria, and so this is finally we repeat that these functions are causal, so they can be represented as automata. And so our optimization of genetic code in the process of evolution was based on causal dynamics. So it is against Koonin, who thought that were just random jumps and they produced genetic code. So this is more or less all. I did not go to mathematical details, and I think in our papers you can read a lot about periodic mathematics, about periodic physics, and so on. Thank you very much for your attention.
Thank you very much. Any questions?
May I ask a question? So I didn't understand the definition of dynamics. So you have, say, RNA, and you have blocks of codons, and then the dynamics is just to change one codon and to see what will happen with the neighbors. Or what is the dynamics?
Yeah, dynamics is, you are right, dynamics is not in DNA. Dynamics is these functions, evolutional functions, the functions which generated this genetic code. So roughly speaking, they work stopped when this genetic code and the structure of attractors was created. So the idea of evolution is the following. At the beginning, for coding of amino acids, the biological organism did not use strings just of the length, binary string of the length 6. So they did not use codons. They used strings of arbitrary lengths, but they used this periodic metric. And there was optimization function. Its origin, of course, not clear. How was it constructed by biology or... And this function started iterations, and more or less it cut these blocks which were longer. They were not important for attractors. Finally, it generates the structure of attractors. So it is not description of functioning of genetic code. And more or less with functioning, of course, its situation is better. It is the model how this structure of genetic code could be generated. Yeah.
Thank you.
More questions, please? If no, let's send the speaker again. Okay. Our next speaker is Professor Ravshan Arturov from Romanovsky Institute of Mathematics, Uzbekistan. The title of the talk is On System of Fractional Nonlinear Partial Differential Equation. Please.
Okay. Hi, everybody. First of all, I would like to thank organizers for giving me opportunity to give a talk in this prestigious conference. So can I demonstrate my talk?
Please.
Maybe this. Yes. Now, can you see that?
Deny for us now. It's fine.
Yeah. Can you see my slides?
Yeah, we see it's in page 9. Is it fine?
Yeah. Yeah, it is not the beginning. Now here we go. Now,
Yes,
I want
great.
to make it full screen. This, I'll try. Okay, never mind. So, but you can see that, right?
Yes.
Okay, so we'll talk about system of nonlinear partial differential equations. So, this is in fact joint work with my colleague Mukhidinova Akila. She is from Tashkent University of Information Technology. This paper was published in Archive in 24 this year. So actually, this work was done when I was visiting Sabir Umarov, and today afternoon you had a lecture by Professor Umarov. So in last 1-2 years, Professor Umarov actively studying the system of pseudo-differential operators with fractional order time derivatives. So our paper is based on the paper number 2 here, which is already published. In fact, this paper 3 and 4 are also published, as today informed Professor Umarov. So consider the system 1. Here, dt is derivatives, so-called Caputo derivatives of order beta. And this AEG, these are differential operators. Unlike the talk of Professor Umarov, here we consider differential operators. So in his case, these operators are pseudo-differential operators, and Professor Umarov obtained representation formulas. And this is, in fact, to study boundary value problems. This is first stage. So we will be also using the results of paper 2. So in our case, H, right-hand side of equations, actually, in general, they can depend on solution itself, U1, etc., UM. So when you have nonlinear equations, then of course you never have representation formula. So, but we will prove the theorem about existence and uniqueness of solutions of this equation, system of equation. Just shortly, I remind Caputo derivative. Caputo derivative defines like this. Here, first you take just classical derivative, then multiply by this function, and then get integration, and then multiply by a gamma function. Here you see, you take first derivative and then integral. If you change, first take integral and then derivative, then you got so-called Riemann-Liouville derivative. In fact, there are many other definitions of fractional derivatives, but more commonly used one, only these two derivatives, Caputo and Riemann-Liouville. When you put here alpha is equal to 1, then you get just classical derivatives like this. In fact, if you take limit alpha tends to 1, then both derivatives are equal classical derivative of order 1. If you take derivative Caputo from constant, say from 1, then you got 0. You can see here, you put here 1, you take first derivatives, then you got not 0. So, but if you take derivative, can you hear me? Can you hear me?
Yes.
Okay, that's fine. So if you take derivative in Riemann-Liouville, here you put 1, you don't get 0, because you first take integral and then this derivative. In fact, you have the following. Actually, because of this reason, in 1960s, they introduced this Caputo derivative, because you see Riemann-Liouville, it has some not good properties. It's usually, we used to know that derivative of constants should be 0. So, okay. And the active use of fractional derivatives began, we can say, from 60s, right? Last century. So why so mostly using this fractional derivative? Mainly two properties of these derivatives allows us to apply these derivatives more widely. First is, some processes propagate more slowly than heat. And in that case, you should take derivative not first order, less than first order, and this kind of processes called subdivision processes. But unlike this, some other process moves faster, and this called superdivision. And in that case, you should take derivative order which is bigger than 1. So, but when you have a classical derivative, you don't have this option. So second more important thing is that when you want to take classical derivative, you should have information about the function just near the point where you're taking derivative, just in very small neighborhoods, because derivative is just this limit, right? And if you know function just near the t0s, then you can know derivative. Unlike this, if you remember here, you see, when you take derivatives, both of them, you should have no information, behavior of function from 0 to t, So that means from the very beginning of process till the end, you should know this information about the function. That's why it's very useful when your process has memory effect. Like Sabir Umarov, they modeled this propagation of COVID. And you see that propagation definitely has memory effect, and that's why they use this derivative, fractional order derivatives. And also, you see, fractional derivative adequately reflect many properties such as memory, hereditary properties of complex processes, which you don't have when you have these ordinary classical derivatives. Now we come back to systems, right? So systems of partial differential equation. Any
Yes,
questions?
one question here. So which definition was appeared first? Is the usual derivative or fractional? Which one was introduced first?
Again,
which derivation was introduced first? Usual definition.
Oh, you mean Caputo or Riemann-Liouville?
Caputo or usual or ordinary?
No, you see, in fact, historically, yeah, when first introduced this Leibniz and others, first they introduced the ordinary derivative. The same time they were seeking about derivative of order half, for example. When they introduced the derivative of first order, immediately there was question, what about the order half? But in fact, the real applications of fractional derivatives starts this 16th years last century. But in fact, the Abel integral equation, that is 200 years ago, he first, in fact, introduced Riemann-Liouville integral and Riemann-Liouville derivatives, but Abel didn't call them like these derivatives. Just he used in his work, but I mean, he didn't mention this name. So this is as old as classical derivatives.
Okay, thank you.
Yeah, okay. Now, so system. there are a lot of work on system of partial differential equations fractional order. And in 2019, there was this paper by Kochubey. This is a review paper. Two papers. First is fractional parabolic equations. That means rho. The order of derivative is between 0 and 1. And second paper is fractional hyperbolic equations. That is, this derivative order is between 1 and 2. So, but I should stop on these works later on when I give our results to compare with these results of Kochubey. But here I would tell that in all papers which is presented in this review paper, the order of differential operators RGK is the same order. But you will see in our case these operators can have different orders. So this is our system. Here you see this AD is like these differential operators. The order is LKG. And with these differential operators, we construct this following matrix. And instead of each differential operator, if we put polynomial defined like this, then you have a matrix symbol like XC here. So using this, if you define U like this vector and H this vector, then our system can be written like this, like 3. Here AD is matrix and U and H are vector functions. Like, you see, we in this work don't want to go to more general case. We want to consider simplest one and obtain the main results. That's why we assume that matrix A is symmetric. This is first assumption. And second is that LGG is bigger than LKG. That means the order of differential operators in this line diagonal is always has highest order. So in this line, highest order is A11, and the last one is AMM. So this is not introduced by us. This is in fact introduced by this condition by Petrovsky. If this condition satisfied, then Petrovsky called this system parabolic system. Okay, so this, and in fact, in Kochubey, they put more stronger condition because their method demands this condition, and they call this strong parabolic equations. So of course, if you have strong parabolic equations, that is also a parabolic equation. But if you have parabolic equation, it's not necessarily strong. So in our case, we have more wider class of parabolic equations. Why we need symmetricity of matrix? Because if you have symmetric matrix, then you can write it like this. So here lambda is diagonal matrix, where this lambda ZXC is eigenvalues of matrix M. M rows of M is eigenvectors of matrix. So we will use this equality. In fact, not necessarily we can do for wider class of matrix. Then I will tell how we can go to more wider classes. So now we introduce. Just recall some Sobolev spaces. This is scalar product in Sobolev spaces. This is Fourier transform, and this is a norm in. And we also this topological direct product of Banach space we use, and then we introduce here the norm as follows. And also, as usual, by this symbol we denote continuous on T functions with values on this Banach space. Now we are ready to formulate our problem. So find functions here in this class, Sobolev class, which belongs to this class. This these derivatives are also continuous and satisfies this equation and these initial conditions. So this is, we call it linear problem. So this definition, in fact, definition of classical solution. If your solution satisfied condition 5, then usually they call it classical solution. Now, one thing here unusual, in fact, when you formulate Cauchy problem, you don't need this condition. U belongs to Sobolev class. But we need this condition because with this condition, we can prove easily uniqueness of solution. This is one hand. On the other hand, when we find solution by Fourier method, and our solution will belong to this class. That's why this class we introduced. Now, later on, I will compare this result with our result with Kochubey results. Then we will see that this is a very good class. So this is just a Mittag-Leffler function, and this is some generalization of exponential function. And the main thing, it has the estimate 9. You see, when you have exponential functions, then it goes to 0 very rapidly, but Mittag-Leffler function just like 1 over t. So this we define the following matrix, and this you could see in talk of Sabir Umarov, and we introduce this pseudo-differential operator, and also the following pseudo-differential operator with this matrix. And now we can formulate, we should introduce the tau star, which is L star minus L star down. L star, this is maximum, L star down is minimum of diagonal orders, okay? And you see, as I told, Kochubey considered in all works, in Kochubey and others, this all operator had the same order. That means LKK is the same. So you put, that means this tau star is 0. If in case of Kochubey, then tau star is 0. So we use these eigenvectors, they are bounded, we use in our consideration. This is the main result about the system. So let XC satisfy condition A, which we told above, and then initial function from this class, and H is from this class, this is right-hand side. In that case, this linear problem, which we formulated above, has unique solution, and this solution has the following form. And also, this solution has the following property. So all tends 0, all derivatives, and also here coercitive estimates. There is a coercitive estimate. You see, I remember someone asked Sabirjan Umarov, do you have coercitive estimates? That so in general case, you cannot obtain coercitive estimates, but in our case, when we have differential equations and then some condition A, then you have this kind of estimate 16. So what means this estimate? It means that if you change H right-hand side a little bit, then solution also will change a little bit. So the same for initial function. If you change a little bit, then solution also changes a little bit. So some remarks. So as I told, if all AGG has the same order, then tau star is 0. That means the condition on phi and H is just like this, L2 tau, where tau is more than half of n, right? So, and this class function, actually, all of them continuous because of Sobolev inbending theorem, right? But the question is, in this condition, can you put here tau equal to n half of n? The answer is not. So this condition is sharp, because if you put tau is equal n half of n, then in this class, there are unbounded functions also. But as we told, in condition of linear problem, these functions must be at least continuous. For in Kochubey theorems, in all his theorems, instead of this class, they demand that this initial function and right-hand side belongs to globally Hölder class and also Hölder continuous and also bounded. So here you cannot say that this condition is sharp, but whereas our condition tau greater than n half of n is sharp condition. You cannot weaken it. This is first thing. And second thing that, as I told, so this condition UG belongs to Sobolev class, ensure that solution is unique. Whereas in Kochubey, the condition is derivative, all derivative of orders 2b continuous and also Hölder continuous. You see, this is to have uniqueness, they put, if you compare with our case, too much conditions, 2b, you know. So this is comparison with the result of Kochubey, not only Kochubey and others also. So now we want to show that from our representation of formula, we can obtain the representation formula of Kochubey. Solution we write as a two sums, V and W, and entries has the following form. And here you see Fourier transform. If you put here Fourier transform definition and change order of integration, then you have the following functions. So with integral form, and kernel has the following form. So that means you can write solution in the form of 21. Exactly in this form, this Kochubey obtained his solution in form 21. So that means from our formula, we also can obtain 21, but you see these functions Z beta and Y beta, in Kochubey case, they use this so-called right function, and this is right function, very complicated function, and it is much easier to have these functions not as a right functions, but through these Mittag-Leffler functions, as in our case. Now this all works, Kochubey here and Bezlikovich, Edelman, Crane, they considered the differential operator this the same order. H, E, G is the same order. In our case, they can have different orders. For example, we can give example. You see, here you take Laplace, and here just first order derivatives. Whereas this example you cannot consider in Kochubey's case. So here we give, we say how we can diagonalize this matrix of this matrix AC, and also we can give explicit form of the solution. So just a few words about nonlinear case. So nonlinear systems, as far as we know, before our work, no one considers. This is, I think, the first one when we consider nonlinear case. So we put the following conditions. This is Lipschitz condition 25. This is usual standard condition for any equation, nonlinear equation, to have solution and uniqueness. Even ordinary differential equations, also you put this Lipschitz condition. And second condition also, it is quite simple condition, because, you know, in fact, this when tau 0 is 0, then this is just means that H should be continuous. That's it. So this is formulation of nonlinear problem. It is just like linear problem. Just the difference is H depends on U nonlinearly, and this is a result from nonlinear case. So the same conditions for initial function. H satisfied two conditions which we give above, and A matrix condition A. In that case, you have unique solution, and unique solution has a property that in infinity it goes to zero, and also we have stability estimates here. So if you have two solutions, one is with phi 1 initial condition, second is phi 2, then different you can estimate like 28 estimate. And also these conditions on H is sharp, you cannot weaken it because of same reason which I told before. And again, as far as we know, nonlinear system is considered for the first time. And I think here some idea of proof, I think no need to stop on this part. So I finished. Thank you very much for your attention.
Thank you very much. Any questions?
May I ask one question?
Yes, please.
Okay, I have basically two questions. First of all, what about this approximation of the solution? Is it possible? Do you have some scheme to solve right now?
Yes, of course. Yeah, of course. This is a very good question. You see, for example, here, you see, we have explicit form for solution. And this integral, this is an example, of course, but you have the same formula for general case. Now you take Fourier transform of initial functions, put here, and just take integral. And integral, you can use any approximation method to calculate this integral. That's it.
What about these generalized solutions? These, is it possible to apply?
Actually, generalized solution is much easier to obtain because you see, what is the difference? I'm investigating this classical solutions. That means I have these integrals, right? And I should prove that these integrals converge uniformly, absolutely, and so on. And I should take derivative and again show that these integrals must converge uniformly. But when I want to investigate generalized solutions, so that is, first of all, this enough convergent in L2. You see here Fourier transform. When you take L2, then you can get it in L2. This estimates very easy. So,
no, but on the other hand, you may weaken the conditions what you did before.
Yes, of course. Yes, of course. You are right. But I didn't do that. But maybe next stage, maybe some students will do. But here, you see, not in this only special case, but in all our works, we investigate for this fractional derivative classical solutions. And there are just a few groups who investigates the classical solutions because, you know, as I told, this generalized solution much easier to investigate. For example, Navier-Stokes equation, you know, already 50 years back, it has a generalized solution, but about classical solutions still open. So that's what. Yeah, but it can be done, but we didn't do.
Thank you.
The questions? If no, let's thank the speaker again. Thank you.
Okay, thank you for your attention.
Next speaker is Karim Rahimov. His title of talk is Dynamics of Henon-like maps.
Yeah, thank you very much for the introduction. It's better to be here. Okay. Okay. Now I'm going to talk about complex dynamics. You know, you all like how I try to be simple. Okay. In complex dynamics, usually we consider complex manifold and holomorphic map from the complex manifold X to itself. Okay, the general question is to describe the orbits of the iteration, like in dynamics. So what happens in the dynamics? The general question. Yeah. Okay, let me define what the Gibbs measure here. Usually we consider it to be compact. Okay, we are given a Bonner bounded function C from x to, usually we consider it continuous function. So, and an invariant ergodic probability measure mu, and define this pressure. Usually we take this pressure here. H nu f is a entropy of the measure. So, and this is just the integral, the second one. So it's the pressure of the measure with respect to this, and we take the supremum by these measures, by all probability, ergodic probability measures on X, which is an invariant, of course. And we say mu is a Gibbs measure if mu maximizes this pressure. So we have P mu psi equal to psi. So usually, okay, when psi is 0, we of course when psi is 0, integral becomes 0. Then it becomes the maximal entropy, the entropy of the dynamics. You take the supremum here, so you don't have this, and in that case you have if psi is 0, mu is the measure of maximal entropy. Usually we call it equilibrium measure. Okay, we mostly consider psi equals 0. Okay, let me talk about the Gibbs measure, the existence and uniqueness of Gibbs measures in complex dynamics. When X is the Riemann sphere, U1, and psi is the Holder continuous, and of course we have a bit more condition to oscillation of psi to the right here. So in that case, there exists a unique Gibbs measure. In that case, okay. In this is by result by Denker and Ubansky, and later Przyczynski, so Tarkiewicz and Ubansky and Dunek proved this result in PK. And my collaborators, Bianchi and Dean, they proved this for the observable block Q control. So this is for comparison. Okay, today in this talk we mostly focus geometry of the measure of maximal entropy, which means in that case psi is 0. Okay, so let me start with simple case dynamics of polynomials in C. So consider this polynomial. So polynomial of degree D. So when degree is 1, it is a linear map. In that case, the dynamics is very, very simple. You can easily calculate. So we suppose in that case, V is greater than or equal to. Okay. So when you see the polynomial, you can find a big ball that's outside of the big ball. That when you do iteration, it goes to infinity. It's easy. You can. So that's why that's why we define this set. Here the iteration is bounded. It's K. So the boundary of this K is usually we call it Julia set of F, and the rest of the set, I mean the complement of the Julia set usually calls Fatou set. Usually the Julia set is the chaotic part of dynamics, and Fatou set in Fatou set dynamics is okay. Here one example for Julia set. I mean the boundary of this set is a Julia set. Together it's K. this K is with this green bar. Okay, usually the Julia type is the fractal, has fractal effect. Today we are not going to talk about it. Of course, let me focus on the Gibbs measure is equal to 0. Okay, how we get that measure? I mean, the measure of maximal effect. In that case, we consider this function. So you take ND, the iteration, and the absolute value, and log plus is just logarithm with maximum with 0 and logarithm. And we normalize 1 over dn. T is the degree of f. Degree of f. You know, Fn is kind of when it goes to infinity, it goes to z power of d power n. So we are normalizing here. So it feels like itself log z at infinity. So this is usually this limit exists, and this guy is the subharmonic function. And gz in the limit exists, and this is also subharmonic function, and it's polar function. Then when you take the Laplacian of subharmonic function, you obtain a measure. So this measure is actually the measure of maximal entropy. This measure. So this is unique in that case, and this has a lot of properties. It's called equidistribution of points, equidistribution of periodic points, and okay, this gives very good information. So we knew that there exists a measure of maximal entropy, and it was unique. But now here we are saying this is C of something. So we know the picture of the measure. Okay, it is in the one-dimensional case. Let me move in higher dimension, dimension 2. Heron maps first introduced in real setting. In real setting, it was okay. It was introduced as a Poincare section of as a simplified model of Poincare section of Lorentz model. Okay, then here later overworked. Okay, later in 1980s, it is also introduced complex case, and they suggest to study the complex case. So in real setting, ZWs are real. So we are considering here complex. When you see this map, when A is the parameter, when A goes to 0, it is like a polynomial. Polynomial is one-dimensional polynomial. Okay. Here in this the dynamics of two-dimensional complex Heron maps studied by many sources. Here it's written. Okay, let me move on. Okay, here, so let's see this again. So in dimension 1, the invertible case is only degree equal 1 in the polynomial degree d. Invertible case is degree equal 1. But when you move to the dimension 2, you have a lot of other maps which is invertible. For example, this guy is invertible. So this is an aptomorphism of T2. Okay, it's the invertible aptomorphism. Okay, so here we define two sets. First, K plus is the forward iteration, is bound. K minus is inverse iteration. Here we can define inverse iteration because F is inverted. So two sets here. So and we take intersection of these two sets as a K, and this is we call field in Julia set, and the boundary of this set is we call Julia. Okay, here again, as in one-dimensional case, we define two functions. These both functions are defined analogously like dimension 1, and these both are fully subharmonic. So in subharmonic functions, again you can take the DC. The DC is well defined positive current. This time it's not a measure, it is a current. Okay, the DC, so we have two currents, T plus and T minus. Now, it was introduced by Sibony. The mu is wedge of T plus and T minus. This is actually this guy is the equilibrium measure. Its unique measure of maximal entropy is this. It's defined. I mean, you can prove that this guy is a unique measure of maximal entropy, and in this form. So here, as we see that we see the geometry of this measure. Yeah, we know how what it is, and even more. Okay, Bedford, Lubitsch, and Smiley and Dujardin, they proved this T plus and T minus actually laminar. Laminar means that this is an average of this kind of lines, one-dimensional lines. T plus T plus T minus. There is no this kind of part. This kind of part. I mean, you see this condition. This condition means there is no a lot of intersection. So this is also giving that more information about these two currents and more information about the measure of maximal entropy. So after this, since these two guys are laminar, then what was mu? Mu was the wedge of T plus and T minus. So mu has local product structure. So and of course this mu is a unique measure of maximal entropy. This was proven by this guys. Okay, this is dimension. Okay, let us see here what happened. We defined what is K plus, what is K. Let us write like this. So there K here, and it has following terms. So you can find a box here, and when you take a smaller box, which I call horizontal box, and when you iterate this guy, it comes to this box. It comes to this box, which is here vertical. So it has this kind of structure. So and what you see here, in some direction it is contracted, in the other direction it is expanded. One direction contracting, one direction expanding. Okay, this one suggests us to define Henon-like maps. Henon-like maps is because there domain D in CP, CK minus P. Here, for simplicity, we take M and N are convex open sets of CP and CK minus P, and we consider this D M times N. We take horizontal domain here, and we consider holomorphic map from this to this, which is from horizontal subset to vertical. And we put the condition that this boundary, this black boundary comes this one, and this guy, these two guys comes to this one. Which means, what does it mean? It means that we have a contracting direction. I mean, K. Okay. We have expanding P expanding direction and K minus P contracting. Okay, this is actually so in two-dimensional Henon maps, P is equal 1 and K is equal 2. Okay, so here when K equal to 2, P equal 1, you obtain two-dimensional Henon-like maps, which also includes Henon maps. This one was firstly introduced by Works under different name, was the plot mappings, and later studied by Dujardin and Dean Gibbs. When P equal K, it is a horizontal like map. This also very big, set of functions which is studied by many authors. Okay, we are not going to talk about this today. Okay, let us consider now Henon-like map. So when you see when I say the Henon-like map, just imagine so you have a holomorphic map from horizontal domain of D to vertical domain. We have P direction expanding, K minus P direction is attractive. So, and now take positive closed horizontal current. Horizontal current means that a current which is support horizontal. The outside is there. Support horizontal. Horizontal current B-dimension PP, and when you study the growth of the mass of this by Fn, so this is actually there exists an integer d that this growth is actually d for n and the times mass of s. This grows like this. This d is independent of s. This d we call is a main dynamical degree of main dynamical degree of. Okay, and so here we took the current of the dimension PP, so that we can consider other currents. Other currents here we consider other currents, which is the B-dimension CC, and we say that this is that dynamical degree D plus C. And also here you see we consider two kinds of dynamics. One is the growth of smooth differential form. DDC, this is just smooth differential form. Here we are considering currents. Okay, two kinds of degrees we are considering. This is important to study the measure, so we are considering this. Okay, also you see this we consider lambda plus C and P plus C. This is for expanding direction. And also we consider one which is for contracting direction, which means we have K minus P plus 1 degrees. This one is defined by vertical positive, the growth of vertical positive. Okay, we have the following property. First, you remember D was the main dynamical degree. So we have this lambda P plus D P plus and lambda minus K minus P and D minus K minus P. They all are equal to P by the definition as well. And we have the second one, lambda plus 0 is smaller than or equal to 1, and D0 plus is equal to 1. And similarly, this is true for D max. Consider this example. This is very simple example. This is a linear map. In this linear map tells us that we really need to be considered this flat, not lambda. we need to work with them because you see linear map is degree 1, yes, 1 to 1 and simple, but this one in that case lambda is smaller than 1. So this example tells us that this is not enough to work with smooth one. The smooth one is not enough. So we need to consider the currents. Okay. Now, okay, in the algebraic setting, this lambda s is ds equal. This is well known. In pk, in ck, these polynomials, they're equal. Okay, in two-dimensional Henon maps, we saw that the plus 0 was 1, yes, we say. The minus 0 is 1, we say. And also we have the main numerical degree in the middle. This one is b, integer. It is or 1 or greater than 1. Okay, it's not 0, of course. Here, it's easy to see that it is kind of monotonic until p, and then it goes down in dimension 2. And in pk, in algebraic setting, this is actually they have even more property. This degree is log concave. Log concave is even better than that property. In particular, you have this d0, d1, monotonic until p, then it goes up. So we expected, firstly expected the same log concavity for Henon lines, but actually this is still open for log concavity of dynamical degrees of Henon-like maps, but we proved this was the joint work with Bianchi and Dean and myself. This is it will published in Transaction of IMS soon. Okay, when we have these two inequalities, so the dynamical degree satisfies this inequality. So we have monotonicity until p. So d plus p is monotone until p, and also d minus is monotone until k minus p, and they are equal to the main dynamical. Okay, why it is very, it is important to have this. Okay, now let us also tell about measure of maximal entropy. Dean and Siboni was proved that there exists the k minus p current T plus and pp current T minus, and such that this guy mu defines the unique measure of maximal entropy. So which means the Gibbs measure with psi equal. So they also proved a lot of properties of this measure, and we now then we study plus and T max. It's another paper with with my collaborator. Okay. Firstly, if you saw here in this case, G plus and G minus, they were Holder-Pack. So we know what the potential, G plus is potential of T plus, G minus is potential of T minus. So potentials was Holder-Pack. That case. Okay, we proved a similar one. Okay. So here you see the condition first. D is we are assuming D greater than maximal of these guys. So from this, if we use our theorem, it shows this that D is greater than all. We have monotonicity. So this theorem guarantees this condition that D is greater than from all others. This is in the P. Okay, if we have this condition, then we have these three properties. First, the green currents T plus and T minus have Holder continuous superpotentials. Then the green currents T plus and T minus are woven. In that case, you can have this kind of intersection. Woven means you may have intersection. Okay. Moreover, this mu is a moderate complement. This is what does mean? This is the DC of something. Okay. And the potential is Holder continuous, and also this measure has positive Hausdorff dimension, which means the support of this measure, the Hausdorff dimension of the support of this measure is positive. Which means this guy positive Hausdorff dimension is this. Furthermore, if P equal K minus 1 and respectively P equal 1, in that case, T minus is laminar. In this case, T plus is laminar, which means in that case you don't have this intersection. Okay, this is so what we give. It gives us the geometry of this measure of maximal entropy. Of course, you can also ask a similar question when psi is not equal 0 for Holder continuous psi and the other, but it's still open. We may work in the future. Okay, thank you for your attention. DDC nima umlashgan mana in the sense of Laplace. DDC is Laplace. Qaytlar. Buna mu demek base product of the current calcium current. Okay, this guy is function, yes. When you take DDC, DDC, it is a current. It's 1-1 current. 1-1 current. We are in the complex case in C2, 1-1 current. To get a measure, you need current. 2-2 current, yes. So you take the wedge product and you get 2-2 current. For example, when you have the line, the complex line, and the integration by this line defines 1-1 current. And if you have another line, this kind of this line and they have some intersection. When you take the intersection, you get here Dirac. So here Dirac A. You obtain a measure. So this guy, this theorem is saying is average of Diracs. So local product structure is the average of Diracs by this theorem. Okay.
Questions? Some questions online? No questions. Thank you. Yeah.
Okay, let us continue our conference. The last talk of the first day is Professor. The speaker is the Professor Victor Bodi from United Arab Emirates University, UAE. The title of the talk is Unitary Units of Modular Group Algebras. Please, Professor Bodhi.
Excuse me, good afternoon. Excuse me, can you see my presentation?
Yeah, definitely.
Yes, is it okay?
Yeah, it's okay.
Okay, thank you very much. First of all, I would like to thank for organizers to give me possibility to present a talk here. Mostly I am working in algebra, but I try to choose the subject which is very close to the C-star algebra, and several problems which I considered here, it can be moved or extended for the C-star algebra. Okay, so let us start. First, we have a classical object group rings KG be the group rings of group G over a rings K. So this is a ring, and this ring has a group of units. So all invertible elements of the rings form a group, and this group is called group of units of the group rings. But in group ring theory, usually we consider it a little bit different group. So let us consider it VKG. This is all units from UKG such that sum of coefficient is equal 1. Of course, in group ring, we consider it only finite sums. So we have only here finitely many alpha G such, finitely many G such that alpha G is not equal 0. And this group is called the normalizer group of units of group rings KG. And there is a formula which is telling that group of units, it's for arbitrary group rings. This is equal the normalizer group of units, direct product group of units of the rings K. So this means that usually we know about over which ring we are working, so it's better always consider it with smallest group, which is called normalizer group of units. So now we have a group ring, and we would like to consider it as a algebra with involution. So let us introduce a map from KG to KG is called involution. If x plus y star is equal x star plus y star, it's anti-automorphism of order 2. So x star star is equal x. And we can ask, can we provide the involution or involutions of group rings? Yes, of course, there are a lot of involutions. So let us give some examples, very important examples. First example, it's called classical involution. For each element from group algebra X, which is alpha G multiplied by G, we define a map to the X star, which is alpha G, and each element G we invert G minus 1. It is easy to verify that this is involution, and I think everybody started with involution in the course of algebras. Okay, now consider the twisted classical involution. So we have the group G, we have a rings K, and we have a map F from group G to the group of units of rings K. Be a homomorphism. For each element X, we define the map almost the same, but we add here like F multiplied by G. Mostly this, and it is easy to check that this map is an involution. So why it's called twisted involution or classical involution? Because it arises from algebraic topology. If we consider it manifold and K is a just integer, So group of units of integer plus minus 1, and FG means orientation. It's orientation plus or orientation minus. For each group ring, we can define the augmentation function, which is for each element X provide the sum of coefficient. It is easy to see that the classical involution preserve the X star involution. So he of X is equal just sum of alpha G. This is equal X star, he of X star. But if we consider it the twisted classical involution, this is already not true. So we do not preserve the augmentation map. Okay, so mostly I am interested about invertible elements of group rings. So using this involution, which I defined before, I will introduce some invertible elements. A unit X from VKG is called unitary if X star is equal X star is X is equal 1. The set of all unitary units is a subgroup of group of units, and it is called the unitary subgroup. And it is easy to see that G is a subgroup of unitary subgroup, and unitary subgroup is a subgroup of a group of units of group rings. A systematic study of the properties of unitary subgroup of group rings was initiated by Adalbert Bode, and some result of his topic can be found in his survey. So this survey was written a long time ago, but this is a short survey and still contains a lot of problem and a lot of information which I will use here. Okay. An interesting application of V star can be found in a paper of Serre. So Serre, in 2014, he wrote a paper in which he found connection between unitary units of group rings and between the Galois extension of finite fields with the Galois group G. So let L be a finite Galois extension of a finite field F, in which F, characteristic F is equal to, and G is Galois extension of this finite Galois extension. Serre showed that there is a relation between self-dual normal basis of L over F and the unitary subgroup of group algebra FG. Okay, now let us consider another example of unitary units, which I will call F unitary units. So let F be a oriented homomorphism, but we can define for arbitrary rings K. And a unit is called F unitary if X, X, F is equal X, F, X is equal epsilon. Okay, there is epsilon from group of units of the ring scheme. When I introduced here augmentation map, I showed that augmentation map is not preserve the involution. So here we need to consider it not only one, we need to consider it all invertible elements. And we can define F unitary units as a set of such F unitary elements. And of course, here we need to consider it all group of units, not normalize it, all group of units. And mostly is a subgroup and called F unitary subgroup. And G is a part of U and F, and this is also a part of this. Adalbert Bode noted that the following two articles of Novikov, which was published in 1917, contains the task of description the invariants of F unitary subgroup for abelian group G. And K was a ring of integer. And these two papers are very famous Novikov papers. So it contains also connection between algebra, some question of Hermitian analog of KT theory and with group rings of abelian group. But now people consider it this much general. They consider it not only abelian group, they consider it the arbitrary groups and arbitrary rings K. And the task of describing the invariants of UF now is called Novikov problem. So I would like to note that several papers and the PhD thesis of Attila Sokach long time ago were devoted to solution of the Novikov problem. So he solved it for some abelian cases. Okay. These two examples shows that article of Novikov and Serre and their connection with unitary elements provide a very good reason to continue studying the properties of unitary and F unitary subgroup of group rings. I would also like to mention that studies of unitary elements in an article of Balogh, his other colleagues here in Emirates, Bartholdi, he used it for some another problem, Gildi, Laszlo Kovacs, Sahai, Robert Sendling, Papas, Sharma. And one remark, if K is a group of integer, if K is a ring of integers, in this case, there is no gap between V star of ZG, the unitary subgroup and G, they are coincide. So it's some interesting things. But if we introduce the twisted F unitary units, it's already G does not coincide, never coincides with UF. Okay, now I would like to show another connection with Lie algebra of the unitary units of group algebra. Let R be an associative algebra with identity. We can consider it R as a Lie algebra if we introduce a new multiplication, a bracket, xy is equal xy minus yx. For arbitrary two subset AB from R, we denote commutator AB, the additive subgroup of R generated by all commutators AB, where A from A and B from capital B. And for any n element, we define the commutator by induction. It's a classical method. So the n lower Lie power of R is an associative ideal generated by all Lie commutators. So, okay, so we have rings R, we can construct it a chain of Lie ideals. So gamma 1, it contains gamma 2 contains gamma 3, and so on. Okay? But there is some small problem. This chain contains Lie ideas, but we would like to work with the associative ideas. How to move this is to associative idea? Very easy. if each such commutator in the right-hand side we multiply by R, we obtain the associative ideas. Two-side ideas, associative ideas. So we have a chain, R with bracket contains R2, contains Ri, and so on. Okay, now we can define, and this is called n lower Lie power. Now we would like to R1 is coincide with R, R2 coincide with these things. Yes, it's the same, R2, but starting with R3, it's a different. So Ri, R multiplied by R. It is easy to see that these two chains are associative ideas, and the first two terms coincide, but starting with the third term, it not necessarily coincide. Okay, so 3 belongs to R3 and so on. Now we can introduce the following notion: lower linear potent, okay, or before it's called, in Russian literature, it's called linear potent. If there is Rm is equal 0, and the algebra R is called upper linear potent, or in Soviet potent, if exists M such that this is Rm is equal 0. The minimal integer M and N such equal 0, and the such bracket is 0 are called the lower and the upper linear potency index of R. And we will L, lower L and upper L. Okay, so what is the relation between these two definitions? Okay, before I will introduce another definition. The algebra R is called Lie hypercentral if for each sequence of elements of R there exists some sequence such that this commutator is equal 0. Gupta and Srivastava constructed an example of the ring R such that lower but upper is never equal 0. So this is a very wide class of the ring. So, and it showed that sometimes happens that the rings can be lower linear potent, but never upper linear potent. Okay, so this example, and we are interested about relation between Lie hypercentral, upper linear potent, and lower linear potent. So there are a lot of examples. But question, what we can say about the concept for group algebra? So about these three definitions in a group, in a case of group algebra. So, and here there is a very interesting result. So let have an arbitrary group G, and let UFG be the group of units. For non-commutative theorem was proved by several authors. So let the following statement are equivalent. Passy-Passman and some co-authors showed that the following three properties are equivalent: A, B, and F. Fg is lower linear potent, Fg is upper linear potent, positive number, G is a nilpotent group, and its commutator subgroup is a finite P group. But in a paper of Bode, Adalbert Bode and Hripta, they showed that conditions C and F are equivalent. So Fg is Lie hypercentral. Also, if and only if Fg is a lower linear potent and it is an upper linear potent. So it looks like equivalence. There is equivalence. And in the PhD thesis of Hripta, very famous result, he obtained the description when a group of units of group algebra is nilpotent. This is equivalent to the following condition. The group algebra Fg is modular and group of units is nilpotent. So A, B, C, D, and F are equivalent. So this is a very surprise result. And this is showed connection between this notion of lower linear potent, upper linear potent, Lie hypercentral, and the nilpotency of group of units. What is the main, how to say, why this theorem is such important? Because when we want to calculate it, the commutator, group commutator in the group algebra, it's a very difficult task. So it can be changed using the state theorem by the calculation of Lie commutators, which is much easy. And my recent result, it's a very surprising, but it looks like that this 1, 2, 3, 4, 5 equivalent to the condition that unitary subgroup is nilpotent. So nilpotency of unitary subgroup, it is a lower linear potency connection with upper linear potency connected, with Lie hypercentral connected, and also I mentioned it before with the Novikov and the Serre problem is connected. Okay, and now I would like to obtain some generalization of this theorem. How we can obtain a generalization of this theorem? Okay, let us ask the Hripta result when UFG is nilpotent. Let us change here to condition UFG is locally nilpotent. What we can obtain in that case? So I obtain the following result, which is generalized result of the Hripta. Let Fg be a modular group algebra of the group G over field of positive characteristic P. The group of normalized units is locally nilpotent if and only if G is a locally nilpotent and G is a P group. Here G prime is a P group, but previously it was G prime is a finite P group. So it is very reasonable extension we obtain. Also, I got this result for non-modular case when characteristic of Fg is not divided. Okay, and the last theorem, it's also very surprisingly. Let Fg be the group of normalized units of the modular group algebra Fg of arbitrary group G over the field F of positive characteristic P. Let V star be the unitary subgroup of the group VFG under the classical involution. Then the following conditions are equivalent. Fg is locally nilpotent, F star is locally nilpotent, and G is locally nilpotent, and commutator subgroup G prime of G is a P group. Okay, thank you very much for your attention, and just I am in the time. Thank you.
Thank you very much for both. Questions, please.
Excuse me, do you open the definition of unitary elements?
Sorry?
Definition of unitary elements.
Okay, I will show you.
This third page, I think.
Unitary here. Sorry, here.
No,
Here.
next. This.
Yes.
In this example one, there is you use the one. This one is one of element, unit element of ring.
Well, in group algebra, yes, I assumed that K be a commutative ring identity. So identity of the rings K and the group G, this is just 1 multiplied by 1. This is the element, we can consider it as an element of K, element of G, and we can consider it an element of KG.
Next. But in the next example, you use the element epsilon between here in this epsilon.
Yes.
What is the difference between epsilon and one in the example
Yes.
one?
If you consider it, for example, field of P elements, yes, it has P minus 1 invertible elements. All elements except 0 are invertible. Yes. So we can consider it also this unitary subgroup here, but this is just will coincide with the unitary subgroup, which I introduced before, multiplied by group of units of the rings K.
Okay, thank you.
But if, because F in P groups, there is no, okay, I want to tell you, you need to have here a subgroup of index UK in group G, because if you have a such homomorphism, you need to have a normal subgroup defined. But in P group it never exists, so there is a reason to define two different types of unitary units.
Thank you. More questions? If no other questions, let's say the speaker again.
Okay, thank you very much. Thank you.
Everyone for participating for the first day of the conference. So today's session are closed. So tomorrow we will continue our sessions. Thank you very much.
Thank you.
Rahmat.
Thank you very much.